Assalamualaikum warahmatullahi wabarakatuh. Okay, I want to continue analysis of indeterminate structures. This time is frame analysis. We are going to analyze frame using stiffness method. Okay, previously we have discussed on truss analysis, so we revise a little bit. In truss analysis, what we need to do to analyze trust using stiffness method, we have to have in the diagram, we have to have number one, node number. Number two, we need to have element number. Element is equal to member, node is equal to join. And number three, we need to label the degree of freedom, number of degree of freedom. This one we label according to unconstrained and constrained system. Unconstrained and constrained system. Number five, we need to put an arrow which is parallel with the element arrow. This arrow is very important because using arrow we can determine where is the near end, where is the far end. Okay, number five is the coordinate. We need to label the coordinate. We will use the coordinate to calculate Cx and Cy. Cx and Cy by looking at the arrow that we put. Okay, this is the basic thing that we need to have in truss. Then we move to beam. Okay, for beam we have to make sure that we have number one, node number. Doesn't matter if we still want to label in terms of ABC. Okay, doesn't matter. Number two, as long as it has the label. Okay, number two, we have to have element number. Okay, element number. And number three, what most important in each type of structure, in stiffness method, the most important thing is the degree of freedom, number of degree of freedom. And again, we need to label the degree of freedom according to unconstrained as well as constrained. But for beam, since beam has same local and global coordinate, so we don't have to put the arrow because the arrow is always going to the right side, understood? And we don't have to put the coordinate because in the formula to calculate K, we don't need to calculate Cx and Cy. Means that the stiffness in the beam is basically based on the length of each member as well as the flexural rigidity of each element. Okay, so now we want to move to type number three. Type number three is the frame. So now we are going to analyze frame. We want to analyze using stiffness method. And in real frame has combination of EI as well as EA. In real situation, it means that when it has combination of EI and EA, means that we have to combine what we have discussed in truss as well as beam in one solution in frame. So in frame, what we need to have, if we look at to the formula of let's look at the formula, the appendix. Okay, let's look at the appendix. So this is the formula. Let's look at the formula together. Okay, so this is the formula. This is the formula. Okay, so in screen right now, as you can see here is the formula for element stiffness matrix for frame. It has six by six matrix. It has 6 by 6 matrix. Okay, it has 6 by 6 matrix. So here we can see in frame it has different local and global coordinate system. Okay, beam beam has beam has same local as well as global coordinate system, and in the equation, in the formula to calculate k for beam, we don't need to calculate cx and cy. That is why we don't need to put the arrow as well as to calculate cx cy, to put the coordinate. Okay, but for frame, so if we look at to the frame, so frame has different local and global coordinate system, and in each node, so as usual, element consists of two nodes. It has near end and far end. However, in frame we can see here that there are 3 degree of freedom per nodes. 3 degree of freedom per nodes. As we can see, I become the near end, and J become the far end, and in each nodes there are 3 degree of freedom. 3 degree of freedom in x direction, y direction, as well as z direction. And we have another 3 located at far end. 1, 2, 3. So both nodes has 6 degree of freedom for each element. Okay, so this 6 degree of freedom, so this is the xyz. Okay, we have near as well as far. So in the formula we have 6 by 6 matrix. Like this. Okay, 6 by 6 matrix like this. So the first 3 column and the first 3 row is actually for the near end. So this is near, near, near. Okay, and the last 3 is for the far end. Far, far, far. Okay, near, 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 far, far, far. So in near nodes, it has x, y, and z. So this is n x and x here, y, z. F x, F y, F z. Okay, same goes to the row here, x, y, z, x, y, z. So in total, it has 6 by 6 matrix. Okay, so this formula is the formula actually to calculate element global stiffness matrices for frame. If we can see in the formula, okay, there are combination of AE and EI inside the formula. AE and EI inside the formula means that in real situation, frame has actually get the effect of flexural rigidity as well as axial rigidity. Flexural combination of flexural and axial rigidity. However, please remember that in frame, basically the displacement in frame occur due to the primary mode of deformation, which is due to the bending effect, means that it is due to EI. So that is why you can see there is a statement down there, okay, for frame where axial deformation are ignored, A is equal to 0. So basically, when we calculate when we want to analyze frame, basically when axial deformation are ignored, or when we need to consider only the bending effect, or we need to consider only the primary mode of deformation, means that A is equal to 0. A is equal to 0. So inside this formula, when A is equal to 0, okay, so it will reduce the complexity of this formula. Means that we can cancel all A, this one cancel. So all AE formula, all the formula containing AE will be cancelled. So basically, after we cancel all AE inside this, what we have is only 4 repetition value. Okay, the formula, after we have consider A is equal to 0, is actually 12 EI over L cube. We have 12 EI over L cube. We also have 6 EI over L square, 6 EI over L square, and then we also have 4 EI over L, 4 EI over L, and another one is 2 EI over L. Okay, so the formula inside this stiffness matrix formula, the value of k will be depend on these 4 formula, the formula inside the stiffness matrix. Okay, it will be based on 12 EI over L cube, number 1. Number 2, 6 EI over L square. Number 3, 4 EI over L. And last is 2 EI over L. Remember, we need to have like this whenever axial deformation are ignored. Number 1, the statement. Okay, it can also A is also 0, is also equal to 0 if we have this statement, or the other statement which has the same meaning is consider bending effect only. Consider bending effect only means we don't need to consider the axial effect. The axial effect is come from EA, so we don't need to consider EA because A is equal to 0. The other statement that can be used to represent the same is, let's say in the question there is a statement mentioning like this: consider the primary mode of deformation. Consider the primary mode of deformation. So if you can see all these statements inside the question, means that A is equal to 0. A is equal to 0. Okay, so we go back to the example, the question that we are going to discuss today. Okay, so this is the basic knowledge that you have to understand is that EI and EA, okay, can influence the analysis, the can influence the result, can influence the displacement value, can influence the reaction value in frame. However, cases, in most cases, A is equal to 0. A is equal to 0. So in the formula, we only have to consider effect. EI effect. So let's look at one frame example. Let's look at one frame example. So I just want to draw the simple frame. The simple frame like this. Okay, consider this one. The simple frame like this, fixed like this. So A, B, and C. A, B, and C. A, B, and C. So it has UDL. Okay. UDL like this. Point load, a horizontal load, uh, subjected at the center of member AB. Okay, subjected at the center of member AB. Let's say the UDL is about 30. Is about 30. This is about 30 kilonewton per meter. And we have 250 kilonewton horizontal load subjected at the middle, subjected at the center of a member or element AB. Okay, so this is, let's say this is 2 meter and 2 meter. This is 5 meter. Okay, in addition to this, I want to put an applied moment. An applied moment which is subjected clockwise. Clockwise magnitude is, the magnitude of this is 350 kilonewton meter. Okay, so let's look at this frame. So we are trying to solve this, to analyze this using stiffness method. Okay, so the procedure will be the same, except we need to put the arrow as well as the coordinate in order to calculate Cx and Cy, because here in the formula we can see Cx and Cy inside the formula. So in order to calculate Cx and Cy, we need to put the coordinate. So we put the coordinate right now. At A it is 0, 0. At B is 0, 4. 0, 4. And at C we have 5, 4. 5, 4. So this is the frame. This is the frame that we are going to analyze. Okay, so first thing to do is we need to divide this. We need to divide this into unconstrained and constrained system, because we need to label the degree of freedom. Okay, degree of freedom, we need to label unconstrained first, followed by constrained. However, in order to check to check the number of degree of freedom in both system, it is it is good if we can base on the unknown reaction in the system. So based on the unknown reaction, we can see that A and C is fixed. So we know that at A there are 3, at C there are 3, so total is 6. So this 6 degree of freedom, so we want to separate it into two systems: unconstrained and constrained system. Unconstrained and constrained system. And from the structure, from the support at A and C, we know that there are 6 unknown reaction. 3 at A and 3 at C. There are 6 unknown reaction. So this 6 unknown reaction is actually represent 6 degree of freedom. Represent 6 degree of freedom because we have 6 unknown reaction. Unknown reaction. We have 6 unknown reactions. Okay, So if we have 6, so by looking at the diagram, there are 3 nodes, A, B, and C. So each node has 3 degrees of freedom. So in total, there are 6 degrees of freedom. And 6 degrees of freedom have been put, they are altogether 9, 9 degrees of freedom. 9 degrees of freedom, A, B, C, 9 degrees of freedom. And 6 have been put in constraint system, means that there are remaining 3, the remaining 3 in unconstrained system, so we need to put the remaining 3 at unconstrained system. So there are 3 degree of freedom in unconstrained system, and this 3 degree of freedom is actually representing 3 unknown displacement, If we want to sketch this, we just sketch this so that we can see the frame under these two conditions. So in unconstrained, we have 1, 2, 3. In constraint, we have 1, 2, 3, 1, 2, 3, 1, 2, 3. The total is 6. Okay, total is 6. So this is located, these two, okay, located at support position. Okay, so the remaining 3, we must make sure that each node has 3. Since there are 6 now, so we have to put another 3 at different position, means at different position like this. Okay, different position. So we have A, B, C. But whenever we want to label the degree of freedom, we need to label start from unconstrained. This is the same with frame analysis, with truss analysis, with beam analysis, as well as in frame analysis. Okay, the way we label the degree of freedom are the same. We need to identify first. We need to identify the number of unknown reaction, because we know that unknown reaction represent constraint system. So the remaining must be put in unconstrained system representing unknown displacement. So we need to label, and we must label the diagram start from 1 in unconstrained system. In unconstrained system, we label 1, 2, and 3. 1, 2, and 3 here. 1, 2, and 3 at B. B is unconstrained because there's no support at B. Okay, and then we continue with labeling 4, 5, 6. 4, 5, 6 for X, Y, Z in A, and continue with 7, 8, 9. 7, 8, 9 at position C. So A and C is actually the fixed support. So after we have determining the labeling the degree of freedom, we go back to the structure. We go back to this. So we can actually put the arrow, because it has combination of EA and EI, right? So arrow. Okay, the arrow, the coordinate have been put. So what we need to do next is, okay, so in this frame analysis, actually in frame there are 2 type of output. Number 1 is unknown displacement. Number 2 is unknown reaction. Unknown displacement as well as unknown reaction. Okay, so in order to determine unknown displacement, we must now understand very well that we determine unknown displacement using stiffness equation. We determine unknown displacement using stiffness equation, or we can also call the stiffness equation as force displacement equation. It is force displacement equation. And in frame, since all members Normally frame has all members with loads, okay, such as member BC subjected to UDL and member AB subjected to point load on the member at the middle of the member. So the formula to calculate the unknown displacement in this frame, okay, the formula is Q is equal to KD plus Q naught. Q is equal to KD plus Q naught. So as usual, K is the nodal forces, means that whatever load that is subjected directly at nodes, we call it as nodal forces. K, capital K, is for the structure stiffness matrix, structure stiffness matrix. Okay, D is nodal displacement and Q naught is equivalent nodal forces. Okay, equivalent nodal forces. So we must use this formula in beam as well as in frame. Okay, in truss we use this formula whenever truss has the effect of temperature changes as well as fabrication error. But for beam and frame, since normally beam has UDL on top of the beam, on the element, frame also has the same characteristics, same criteria. So we must consider Q naught in beam and frame for determining the far end reaction, and we distribute equivalently to the nodes. Okay, so as usual, as I always mention, so set in your mind, you have to understand that we have to set our goal before we start doing this, before we start analyze this. So what is the goal? The goal is the objective. What is the objective? The objective for this question, for frame analysis, number one, we have two objectives. Objective number one, using we analyze frame using stiffness method to calculate unknown displacement. Means that unknown displacement is the first objective. So how to calculate unknown displacement is by solving the stiffness equation. So this is the stiffness equation. Okay, number two. What is objective number two? Objective number two is unknown reaction. And we can only determine unknown reaction after we have determined the unknown displacement. And unknown reaction can be determined by using multiplication. It is matrix multiplication. Okay. So step or procedure as usual, the procedure. So procedure, for the procedure, okay, for the procedure, because we know that we want to solve for the unknown displacement, we have to have the stiffness equation. So I have explained to you previously that we need to skip unnecessary step. Unnecessary step if the question just asking us to determine unknown displacement. However, if the question asks you one by one, for example, step number one, we need to establish element global stiffness matrices. So this one is compulsory. Element global stiffness matrices is compulsory step. Matrix or matrices, because we have more than one element, okay, to become structure. Okay, element global stiffness matrices, element global stiffness matrices. Okay, this is the compulsory that everyone should do when you want to analyze frame. Step number 2, from element global stiffness matrices, we will have the stiffness matrix. The stiffness matrix. It is called as structure stiffness matrix. Okay, this is the second step. However, this step in full, it is not necessary to give, and unless the question asks you to do so. Okay, in full means that 9 by 9 matrix. Based on this question, we have 9 by 9, 9 by 9, 9 by 9 matrix, 9 by 9 matrix, and this K which is 9 by 9 matrix is not compulsory. It's not compulsory unless the question asks you to do so. Okay, so this is not compulsory. So what is compulsory? Okay, what is compulsory? Okay, the compulsory step is we need to have the structure stiffness matrix corresponding to unconstrained degree of freedom system, because we know that in unconstrained system there are unknown displacement. This is not compulsory. We can have K, but we just need to have K which is equal to 3 by 3. 3 by 3 representing unconstrained degree of freedom. Okay, 3 by 3 means 1, 2, and 3. Okay, however, we can also skip this step because we can put all the K value, K due to unconstrained degree of freedom system, directly in the equation. Okay, so we move to number 3. Step number 3. So for frame, so by looking at this frame, okay, this frame, so let's look at member A, B, and as well as member BC. Member AB has loading on the member, subjected to the member. Okay, and member BC has UDL. Of course, UDL is the member with load. Okay, so nodal forces is whatever force that is subjected directly at node, such as moment at B. That is nodal forces. But when we have like a 250 kilonewton subjected at the center of member AB, so this one is actually called as equivalent element nodal forces. Means that we have to distribute this 250 kilonewton equivalently to the nodes. Same goes to member BC. Member BC has UDL of magnitude 30 kilonewton per meter, and we need to uh, to analyze this using the formula, and we have to divide this value into the equivalent element nodal forces. We will use the formula given in appendix page 3. So the next step is, so what is important to analyze the unknown displacement for this frame is we have to establish equivalent element nodal forces. This is just like the step to analyze beam. This is just the step to analyze beam forces. This one is Q1, Q01, and Q02. Okay, Q0. The small letter is for the element, and capital letter is for the structure. So we have we have, after we have determining q naught 1, q naught 2 for element, we have to determine or establish as well equivalent node, sorry, yes, this is correct, equivalent nodal for, so this one is for the structure, this is for the element. Okay, structure, this one is element. That is why the word it has the word element. Equivalent element means that the value for each element, and use that value to produce equivalent nodal forces, and the symbol of this one is q naught, q naught, capital Q naught. Okay, we put the naught to differentiate between q nodal forces, and this is q naught, equivalent nodal forces. Okay, is it okay until now? So after that, we have to apply the stiffness equation. Uh, if the question asks you to give in full, establish stiffness equation, you have to give in full. Means that Q1 until Q9, K until 9 by 9 matrix, D1 until D9. And then Q naught 1 until Q naught 1 until Q naught 9. However, it will be depend on the question. If the question doesn't ask you to give the stiffness equation, it is just asking you to calculate unknown displacement. So we just need the stiffness equation. We just need the stiffness equation corresponding to unconstrained degree of freedom system. Okay, stiffness equation corresponding to unconstrained degree of freedom system, which is q is equal to kd plus q naught. So our task now is to find whatever value to fill in this one. K, D. Okay, this one means that we want 1, 2, 3, 1, 2, 3. This is also 1, 2, 3. So this is actually D1, D2, D3 as the unknown in this stiffness equation. So we have Q1, Q2, Q3. So Q1, Q2, Q3, we can refer back to the main diagram, Q1, Q2, Q3. Q1 means horizontal force, Q2 means vertical force. So there is no horizontal force and vertical force at B. So the value for position 1 and 2 is 0, 0. And we have the moment at B. Moment at B is 350 clockwise, and this is opposite with sign convention. Remember, sign convention for stiffness method is counterclockwise. So it is negative 350 kilonewton. Negative 350 kilonewton. So we have to have K to put all the K, all the value inside the stiffness matrix. And we need to put the Q naught value for position 1, position 2, and position 3. And in order to do this, we must have step number. We must have step number 1, and we must have step number 3. Step number 3. Okay. Can we move further? So now I want to show to you how to, okay, the procedure step. Yeah, we do it step by step, but I don't want to show in detail value because it is actually same analysis Same procedure, same with beam analysis, except the degree of freedom become 3 for frame. So the procedure is the same. So this is the step. This is the step. Okay. Step number one. Step number one, this frame has two elements. This frame has two elements. We can put AB as element number one. This is element number one. And element BC or member BC as element number two. Element number one, element number two. Element number one, the length is 4 meter. Element number two, the length is 5 meter. The length is 5 meter. So, we have 6 by 6. We have 6 by 6. So, we will have K1 and K2. We have two K1 and K2. K1 and K2, and of course the matrix for this is 6 by 6. So this is 6 by 6. Matrix same goes to K2, 6 by 6. 6 by 6. 6 by 6. Because 3 belong to near end and another 3 belong to far end. Okay, let's look at the label. Element number 1. Element number 1. Okay, element number 1, A is the near nodes. We determine this from the arrow. And B become the far node, near node and far node. Okay, let's look at the label. Okay, the label for AB for near node is 4, 5, 6. 4, 5, 6. B, the far node is 1, 2, 3. So it is 4, 5, 6, 1, 2, 3. 4, 5, 6, 1, 2, 3. So we just have to calculate the value by using the formula and we put inside this bracket. Okay, the label is 4, 5, 6, 1, 2, 3. 4, 5, 6, 1, 2, 3. Okay, 4, 5, 6, 1, 2, 3. 4, 5, 6, 1, 2, 3. Okay, if we look at to the element number 2, B is the near node, C is the far node. We identify far and near based on the arrow. The arrow we put in any direction that we like. So we have, if we check for the, okay, this cache. So at B, 1, 2, 3, at C, 7, 8, 9. 1, 2, 3, 7, 8, 9. So we have to put it here. So this is 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. So I don't want to put all the value in detail in this step because all this value we can find or we can calculate using formula given in appendix. Okay, so what I want to highlight now is the equivalent element nodal forces. Actually it is actually the same with beam, except this one is 3 by 3 at near nodes, 3 another 3 at far node. So the position is just like K. The position is just like K. So we will produce Q node 1, which the value, the position is equal to K. 4, 5, 6, 1, 2, 3. Okay, and for Q node 2, okay, we have 6 value because the label for the element, equivalent element nodal forces, the position will be based on the K. So here is 4, follow this K2, 1, 2, 3, 7, 8, 9. Okay, it is 1. So don't forget, don't forget. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. Okay, so now I want to focus to this one only, because after getting this, I believe that every one of you can continue until the end. So I just want to highlight this. Okay, so remember that we need to use the fixed end reaction formula. Remember that this fixed end reaction, including fixed end moment and the vertical reaction, is actually the reaction or the behavior of the beam after loaded. Okay, so for element number one is the vertical element. The vertical element. So remember that this is actually the what we call this is actually, okay, so this is actually the element number one. Element number one, this, remember that this is behavior. This is behavior. So if a load is subjected like this, loading is subjected like this, okay, the value is 250 kilonewton. 250 kilonewton. So what we need to do is, it is just like this. It is just like, okay, so this is A, this is B. Remember that the beam will bend. This one is column. This one is column. So we can actually draw it back in this direction that you familiar. So this is 250. 250. Here is A. Here is A. Another one is B. Okay, for the reaction, for the vertical force to be balanced, so we have 125, 125. So this is 125 in opposite direction. In opposite direction. So this is 125. Because we need to balance back. So the value is 125, 125. Okay, for the fixed end moment, moment always acting like this for, okay, like this for fixed ended beam, and we need to use formula W. This one is not W, this is PL over 8. PL over 8. PL over 8. P is 250. Length is 4 meter divided by 8. It is also equal to 125. So the value is also 125. So this is 125, 125, 125. So at A, the moment is counterclockwise. At A, the moment is counterclockwise. At A. At A, so where is A? Clockwise. Okay, at B clockwise. B clockwise. B clockwise. We need to imagine like this. Imagine like this. Okay, imagine like this. So at A moment is counterclockwise, and at B moment is clockwise. So this is for the equivalent element nodal forces. This is element number 1. Means that after having this, what we need to have is this one. Label. So it is, refer back to the diagram. Okay, this one. It is 4, 5, 6. 4, 5, 6, 1, 2, 3. It is 4, 5, 6, 1, 2, 3. Okay, so here is 4, 5, 6, 1, 2, 3. Okay, so we compare these two. We compare these two. We compare this one. We compare this one, as well as this. We compare these two, so we can write the value for Q not 1. Q not 1. Q not 1. There are 6 value. Okay. So Q not 1, the label Q not 1, 4, 5, 6, 1, 2, 3. 4, 5, 6, 1, 2, 3. 4, 5, 6, 1, 2, 3. Okay, so we can put now the value. So we compare these two diagrams together. At position number 1, it is negative 1, 2, 5. Negative 1, 2, 5. Okay, same with, okay, the green highlight. Okay, the green highlight opposite, it is negative 5. So okay, here also. Okay, 1. That one is 1. 1 is negative 1 to 5. 1 is negative 1 to 5. 4. 4 is also 4. 1 4. 4 is here. 4 is here. So both 1 and 4, the value is negative, is 1 negative, no, both are negative because the reaction is opposite. The reaction is opposite with the sign convention, the degree of freedom numbering. Okay, so 1 to 5. Okay, let's look at position number 5. Position number 5, the value is 0. 5, 0, 2 also 0. And number 6, 6 clockwise, okay, 6 clockwise, same direction, it is 1 to 5. 1 to 5. And then for 3, where is 3? Opposite. It is opposite negative 1 to 5. It is negative 1 to 5, like this. Okay. 1 to 5. So this is for element number 1, the vertical element. So we get like this. Okay, we get this. So we move to element number 2. Element number 2, we have what we have now is, okay, let's look at back to the diagram. UDL length is 5 meter. UDL line length is 5 meter. So member BC. So this one is member BC. So member BC, the diagram is like this. This is 5 meter. Moment acting like this. Vertical force acting like this. The value is 30 kilonewton per meter. Okay, so it is 30 or 300? It is 30. Is it right? Is it right value? I have given to you early today. 30. Okay, 30 kilonewton per meter. 30 kilonewton per meter. Okay, we check the value. Check the value. Okay, it is 30 times 550. It is 75, 75, and the moment is WL squared over 12. W is 30, L is 5 square divided by 12. So we get 62.5. So both has 62.5, 62.5. So we need to compare. We need to compare with. We need to compare with this one. Okay. So we have to compare with this one. So the label for this is 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. So we compare these two. We can compare these two and we will get Q not 2 is equal to, okay, label outside will be based on the, okay, on this one. Okay, will be based on this one. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. So we compare this. We compare this 1, 1 and 7. The value is 0. The value are 0. So 1, 0, 7 also 0. Okay, number 2, where is 2? 2 is 2 and 8 is the vertical. It is 75, 75. 75. And for moment compared to positive, we have to compare. So it is positive 62.5 and negative 62.5. Negative 62.5. Okay, so what we need to do is we have to plus this 1, 2, 3 and 1, 2, 3, and we have to put into the equation. We have to put into the equation. So we have equation Q is equal to KD, D1, D2, D3, okay, D1, D2, D3 plus Q naught 1. Okay, Q naught 1 is 1, negative 1 to 5. Negative 1 to 5. D2, where is D2? Okay, D2, for D2, position number 2, 0 and 75. So it is 75. 75. Okay, next, last one at position number 3. At position number 3, okay, at position number 3, moment, at position number 3. So we look at this one, negative 125 plus 62.5. 125, it is negative 125. Negative 125 because okay, in Q naught 1, negative 125. 1 in Q naught 2, sorry, it's not 1, this is 3, negative 125 plus 62.5, plus 62.5. So it is equal to negative 62.5. Okay, so here is negative 62.5. Okay, so what we need to do is like this. Okay, so the difference between beam as well as frame analysis is only okay, it's only for this. Okay, based on this is equivalent element nodal forces. So what we need to do is we have to draw the free body diagram of fixed ended reaction, and then we need to compare with the label that we have put early. So compare these two, whatever opposite with opposite, we have to put negative. All right. So I just want to show to you until this step, because I believe every one of you can fill in this with value. Fill in this with value. So here is 0, 0, negative 3, 50. Okay. The 0, 0, negative 350, D1, D2, D3. Okay. And then Q note 1, Q note 2, Q note 3. Then after we get K value at position 1, 2, 3, 1, 1, 1, 2, 1, 3 until T3, we can solve this by using simultaneous equation with three unknown. Then by solving this, we will get D1, D2, and D3. Okay. Okay, so I think that's all for this session. I believe every one of you have actually understand trust and beam. So basically, frame analysis will be similar with beam analysis, except for the equivalent element of the forces. However, doesn't matter. When we don't have the value like this, we just have to put 0. Okay, so we get this one, and when we have K value, we put into this, and then we will use calculator directly. We will establish or determine D1, D2, and D3. D1, D2, as well as D3. Okay, after this, dah dapat D3. Once you have determined D3, so we have to continue, use D3 back, put into the matrix stiffness equation, and then we try to solve for the unknown reaction. Okay, so I think that is all for this time. Inshallah, we will continue with some more exercises, especially for thrust and beam, as preparation for your test this Sunday. So I wish you all the best. Continue doing exercise. Inshallah, everyone will succeed. So that's all. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.